Hey guys, the topic for today is relative motion or frame of reference. Now, this topic can be a little bit difficult conceptually, so I'll make sure that I'll go through it as possible, as clear as possible. And I've also made my own notes about it and how to solve certain problems. So let's start with this picture. So the train is moving 15 meters per second east, and the man inside the train is also going 1.2 meters per second east. So if you're standing on the ground watching the train go by, relative to your position, how fast does it look like the man is walking? Well, this is luckily this is one of our simpler problems or our observer problems. So I see that both vectors are going the same direction to the right, and so I'm going to add those vectors. 1.2 plus 15 is equal to 16.2 meters per second to the east. So velocity of moving objects with respect to other moving or stationary object is called relative velocity. And this motion, we call it relative motion. So we're going to say it's relative to certain positions or certain places. So in this problem about the man on the train, what was the reference point? Well, the man was the reference point, because in the end, in the question, we want to know from the relative position of the man, how does it appear that the man in the train is walking? When we talk about velocity or something, we first determine a reference point, and then according to the reference point, we say the velocity of the object. Okay, so the only way to really go through this is to go to some practice problems. And before we get into those practice problems, I made some, a little bit of a cheat sheet on how to define or solve these problems for frame of reference. So for example, let's say your frame of reference is an observer, or you're on the ground, because usually the observer is on the ground, or you're on Earth. Okay, or sometimes they'll say the riverbank, or down by the river. Usually it's stationary. Riverbank. So then we're going to add or subtract vectors like normal. So if they're going the same direction, I'm going to add them like this. If they're going opposite, I'm going to subtract. Now, if my frame of reference is an object moving, or when I say two moving objects, then if they're coming together, I'm going to add the velocities. And that makes sense because for example, maybe in a collision, you would think you're going to start, as you're going towards each other, it looks like you're going faster and faster. As opposed to if they're both going the same direction, and maybe you're trying to see the frame of reference from this person, then it looks like you're going slower. So it's going to be subtracting velocities. Okay, and I'm going to revisit this as we solve the problems. But if you'd like to add this to your notes, you can. Let's go back to the problems. So plane A, so it also helps to draw these out. So plane A is traveling 400 kilometers west. So we have a plane here, and it's going 400 kilometers per hour west, compared to a reference point on the ground. So somebody on the ground is watching. Plane B is also moving the same direction with the same velocity. So we have two planes compared to the same reference point, but it is 100 miles east of plane A. So they're separated by 100 miles. Using plane A as a reference point, so notice it's taking this as a reference point. And that reference point is moving. This is moving. What is the velocity of plane B? And this is also moving. So I call this a two moving objects problem. So if you look back at I'm going to go back to this real quick. If we have two moving objects, I'm not sure if you can see this. If we have two moving objects and they're both going the same direction, I'm going to subtract the velocities here. Okay, so Let me go back. So 400 minus 400 is going to equal 0. And that makes sense if you think about it. They're both going the same speed. So even that person, they're both going the same speed. It's going to look like they're not moving at all. And so it makes sense in that. Okay. Next problem. So you're riding on a bus. Okay. Here's my bus. And it's going 50 miles per hour forward relative to a sidewalk. So here's a sidewalk. Oops. Okay. And you decide you want to change seats to the front of the bus and you walk forward. So here you are on the bus. Okay, and you decide to also move forward 0.1 miles per hour. Okay, how fast do you appear to be moving to a person watching you from the sidewalk? So this person watching you from the sidewalk, this is your frame of reference. So this is the observer. They're on the ground. So these are the easy problems. I like these because this person is just watching you. So if they're both going the same directions, just like in our very first problem, then we add them. We add them together. So we have 50 plus 0.1, that is 50.1. So if you think you got the hang of it, try the next few problems. Pause the video and then I'll go over the new problems. Let's see. Let's go over the last two problems here. Okay. So a boy in a canoe paddles upriver at a speed of 1.4 meters per second relative to the water. So first of all, let's draw this. Let's draw this out. So let's say we have a river here. And somebody's canoeing upriver 1.4 meters per second. The water flows downriver at a speed of 1.4 meters per second. So this person is going against the current. They're going opposite ways. How fast is the boy's canoe? This was the boy. Appear to move when viewed by an observer standing on the riverbank. So let's say the riverbank is here and somebody is standing by the riverbank watching you. Okay, so this is an observer problem. That means that we're going to just add or subtract vectors like usual. So this person's watching you and he looks, you're going to the left and the other one's going to the right, or up and down, they're going opposite ways. So we subtract them. 1.4 minus 1.4, that would be 0 meters per second. Okay. Let's try this problem now. So you're running on a boat that's moving at a speed of 20 meters per second towards the north, relative to the river. So here's our river again, and you are on a boat that's going 20 meters per second. Relative to the river that is flowing 5 meters per second to the north. So the river is also flowing 5 meters per second. So that's good. You're going with the river. So how fast are you moving while sitting on the boat? And this should say relative to river bank. So somebody on the side is watching you, or could be watching you. So here is this person, my horrible drawings. So this person's watching you and they're both going the same direction. These vectors are going the same direction, so we add them. So 20 plus 5 is 25 meters per second. Now B, how fast would you be moving if you walk to the south at 1 meters per second? Okay, so we imagine you're moving back at 1 meters per second. Well, you're originally going 25 meters per second, and then you decided to walk south opposite, right? Because this person's still watching you. So you're going opposite, so I'm going to subtract 1 meter per second. So you're left with 24 meters per second left.